All right, I guess we can start it. So I apologize for bringing you here in this inconvenient time because I'm going overseas travel next week, so I couldn't do the class on Wednesday. And later on, such a thing probably will happen again. But in that case, I'm going to invite some guest lecturers. But I'm trying to do the guest lecturing as few as possible because just to keep the whole style of the class coherent. So today we're going to continue our discussion on some interesting instances of graphical models. Okay, so and today's model is a very interesting one. We're going to talk in depth about this thing called conditional random fields. This is invented in this place, in this very place, by John Lafferty, and it is one of the most widely used graphical model nowadays in many applications. And I read the first kind of version of this work about 12, maybe 13 years ago when I was a grad student at Berkeley. And that paper was really difficult to understand. I have to say that the whole Michael Jordan group spent a good amount, 2 or 3 weeks, just in understanding the very mathematics and all the background and the applications of this model. Now you look backward, you see the whole thing was very straightforward, thanks to the widespread practice of graphic models. But I hope you still find some of the motivation and mathematical underpinning for this model intriguing and interesting to understand. So before I do the model, I'm going to again begin with a kind of a small background survey and also a review of what we learned so far in sequential model. Okay, so remember last time we talked about the common filter, which is a sequential model in which there are hidden states which are continuous. And the hidden Markov model is a similar graphical model, except that now the hidden states are discrete. And I kind of use this model as a running example in many of our earlier lectures in inspiring the representation, the inference algorithm, and the learning algorithm. So now I'm going to do a very quick dry run so that you all are converging to the same kind of picture about hidden Markov model, a complete one. Right, so this is a model. And this is probably our last time to review the whole graphical model nomenclature. Then we're going to move on and assume everybody is a master of that. So to define a graphic model, we need to have a graph. That's basically we draw it here based on our structural knowledge of the domain. And this one, of course, is debatable whether it is correct or not. But suppose that we don't want to enter this debate. We just like a particular graphical model. And then starting from there, you can bring in the parameterization. Right? For this one, we need the marginal distribution of the node, of the root node, and then some conditional distribution of other nodes given its parent. And here, we choose to use a multinomial distribution to define all these conditional distributions. And here you have 2 important pieces. One is called a transition probability, right, which is parameterized by a matrix. Every row in that matrix is a multinomial for a particular state going to all the other possible states. And if you put all these states together, you get a matrix A, right? So this one basically, gets to an A matrix. And this is the ijth element of that matrix. And then we need to have the start probability, that's in here. And then we need to have an emission probability to define the conditional probability of x given y. And depending on x being discrete or continuous, we can use a multinomial or a Gaussian, right, or other distributions. And in the case of multinomial, this one actually goes to a matrix B, in which again every column in that B is the emission probability of from one state to all the possible emissions. You will find all this matrix representation very handy down the road when you actually code up your program, because a matrix manipulation can simplify a lot of the operations. Once we have that, we knew that there are important inference problems to ask on the hidden Markov model, And we talked about two algorithms. One is called the forward algorithm. The other is about the backward algorithm, which basically take a recursive form, right? The forward algorithm, is computing this forward message alpha, okay, at time t for state k, which can be computed from this recursive equation from the previous alpha, right? And also some other numbers. And in the broader message passing or belief propagation context, I hope you still remember this alpha message corresponds to the forward message sending from time t to time t minus 1 to t, right? Which actually has its own probabilistic meaning. It is the joint probability of a half sequence plus the ending state. And likewise, you can say similar characteristics about a backward algorithm, which is also recursive, and the backward algorithm computes a backward message, which is defined in here. Then, there is another key quantity that we want to compute, which is the conditional probability of any given state given the entire sequence. And this particular quantity can be actually computed by a dot product of the forward message and backward message meeting at time t. Okay, so this message is sometimes called a gamma message, and in here, gamma message actually is related to another message called psi. By marginalize all the states for j. J basically you will see what is psi. Psi basically is this joint probability of a pair of hidden states. Yt and yt minus 1, okay, and plus the entire sequence. So what is the utility of this message, if you still remember, or this particular quantity? Why we need? We have the marginal probability here. We have some interesting conditional and the joint probability here. What is the utility of this particular quantity? So I'm trying to help you to put all the pieces together to form an entire picture. You want to actually, have a very coherent and complete picture about every elements in this whole system hidden Markov model, right? So here, if you remember, when you want to learn a hidden Markov model, you use a EM algorithm on a Bound-Welsh algorithm, in which you need to compute the expectation of a pair of states. Remember that? Right? If you remember that, then you probably realize that to compute the expectation of a pair of states, actually yt plus, then you need to have the marginal probability of these two states given a sequence, right? And that is not directly computable from alpha and beta yet. So here I'm giving you the equation, the formula, right? It is basically, remember our definition of a bigger message, the definition of the marginal. The marginal basically is a function defined on a clique, right? And it should take all the messages coming into the clique plus some local terms, right? So here I'm going to now put together this forward message coming into this clique, and this is the message coming also into the clique from the tail end, and then the other terms included in this clique. So in this clique we have a y1, a yt minus 1, and a yt. Right? And subject to normalization, they give you the conditional probability of a pair of states given the entire sequence. Right? So I want you to be familiar with all this manipulation, so that eventually every quantity in the hidden Markov model can be computed. For example, in case you want to compute, for whatever reason, yt minus 1, yt, and yt plus 1, how do you do that? Right? Basically, it will be a message into this three-element clique, and a message from here into that three-element clique, and then all the local terms, which includes two transition probability plus some emissions. Right? So that's basically something I want you to reach, a level I want you to reach. Not only remembering the thing that I wrote on the board, but also be able to, extrapolate or instantiate similar examples. Yes?
What if the y's are not conjugated?
What the y is not?
Not conjugated.
if they are not contiguous, yeah, that's a very, very good question. If they are not contiguous, you can. In fact, that's a very, very good question. If they are not contiguous, you have to, find a bigger clique, okay, and then which include everything, and then marginalize something in the middle, okay. But if you put these things down first, and see what the message is, like what elements in this product is, you may find that the marginalization of something in the middle may be a local operation as well, because they are, after all, just pairwise terms. And once you manipulate all the summations, and with what we did in the elimination procedure, you may be able to simplify that computation, right? So the key kind of a skill I want you to kind of acquire is that you need to establish a good kind of relationship between the computation of some chosen marginal of some chosen subset of variables, which we call query, and against the stuff in the probabilistic database, which are the messages that you generated from this graphical model. Okay, and then you can manipulate. And so here I wrote it in the explicit way, replacing the message with their actual mathematical expression, which actually boils down to a alpha message, a beta message, and then plus some other terms. And here I want you to give a small tip, which will help you write efficient MATLAB code or even C code if you have a good library for this type of operation, right? So in here, it looks like you need to enumerate over a lot of things. So here, K is the alpha state at a time t for a particular value of y equals to k. And here you need to sum over all the possible values of alpha at time t minus 1. This is actually a computation which happens to all the state that you care about. So you can actually imagine the alpha is actually a vector, okay, which contains alpha t1, alpha t2, and all that up to alpha t capital K, and you don't have to actually iterate over each of these. You can treat them as a single vector, and then once you want to update this vector at time t from a vector at time alpha t minus 1, you actually have a systematic way of updating that. Okay, how do you update that? Well, first of all, you can see what is this. This is a transition probability, right? Transition probability from I state to K state. Okay, that basically tells you that I need to have a transition matrix in which if I worry about state 1, then basically I need to use the first row in this transition matrix to be dot product with this alpha to generate this part, right? So this whole thing basically will produce a vector, okay? Each correspond to a particular row in that message. And then outside of that, for every corresponding little k, you have to multiply a emission probability resultant coming out of the state k, right? And how do you do that? Well, here you put up another vector, which is this emission vector b. But in that case, it is not going to be a dot product, right? It is an element-wise product. So you kind of put something like this. And that's why I wrote it in here, right? You have the first matrix dot product, and then element-wise product with b. And you can do the same kind of arrangement for the beta message calculation, the psi and the gamma. And all this basically becomes a single line in the MATLAB code. Right? So this is a very handy. That's why I say the entire hidden Markov model inference algorithm will take less than 10 lines of MATLAB code. In this case, 4 lines did everything, basically, except maybe a for loop. Actually, here, the only loop you need is the t loop, which is to loop over all the t's, right? All right, so that's basically the whole picture of hidden Markov model. And then once you do the inference, you know how actually you do learning, because in the learning case, we already said there are 2 scenarios. One is supervised learning, the other is unsupervised learning. And for supervised learning, it's very straightforward. Maximum likelihood estimation of any multinomial parameter is basically the sample average, the sample mean, the counts. Right? So you basically do this, counting of transitional events divided by the events that is transitioning out from the state, and then you basically maybe apply some smoothing technique, if you will, to avoid a zero probability. You can add a pseudo counting here. That's up to you. And if it is continuous, you should know how to do that already, right? The transition probability will be the same. And for continuous, this one is no longer a multinomial. It's going to be estimating a condition-specific Gaussian distribution or something else. You're going to basically, again, do what you did in the in the Gaussian density estimation, right? To put together all the samples from the same Gaussian, and then compute their corresponding mean and covariance. And when the hidden states are unobserved, okay, now we know everything. That is straightforward. We actually are going to deal with the complete likelihood with a expectation over the hidden variables, so that this whole thing is still decomposable. And then you have all these nice equations where the counts of hidden events will be now replaced by the expected counts of the hidden events. The expectation come from our inference problem, which computes the conditional probability of latent state given the observation. Okay, so that's basically a very quick dry run of hidden Markov model. I'm not going to talk it anymore, and I hope you at least get this model straight, so that you can. I think I remember when I was finishing my first year graduate at Berkeley, I need to go through a qualifying examination, which is not happening here, and I was asked to derive HMM on the board, like in 3 minutes. But if you know all these tricks, it's becoming pretty straightforward to derive that. All right. So now the development of science is always like you develop one thing, and the second day you say it's no good, and then you want to do something new, right? So now let's investigate a little bit about the shortcomings of hidden Markov. We said so many nice things about HMM, but indeed there are a lot of limitations as well to HMM. One of the major complaints people had for HMM is that, on every stage, by definition, it is going to generate a very localized observation. Okay, so if you imagine this is a natural language application, then that means here, you can only generate a single character or a single word from a given state, which kind of also said that at least directly, this guy is going to be only dependent on this guy. They can depend on other guys indirectly, but that's beyond your direct modeling power. You can not express, for example, how other features in a text influence this one, right? It is beyond your control, even though that influence can happen indirectly. But the truth is that people actually realize, even for NLP application, all these hidden states, are very often not only depend on a local feature. For example, there are some non-local features such as the whole length of the line, right? The indentation and the amount of white space, and whether you boldface a word or a italicized word. All these actually could influence your way of putting a tag, part of speech tag, on these latent states, right? So how that kind of property can be, I would say, explicitly captured. They are not implicitly captured. Because once we do a forward-backward algorithm, the conditional probability of this guy does depend on everything else, but it's very indirect. You do not have a way to encode your knowledge about that. So, and also the other issue is going back to the Vapnik argument about being parsimonious about learning, right? We visit this story already when we debate between a naive Bayes and a logistic regression. We said that if our goal is to predict why we care about kind of learning the joint of x and y, and then use a base rule to write down a posterior. We could just directly write down a p of y given x, right? And in HMM, such a thing is not allowed. So with that in mind, again, at the turn of the last decade, actually, I think it's the turn of the last century, people started, looking into this problem. And there are some detours, began by a kind of a wrongish model, which is named in here. But just a few months after publishing this model, people realized that it is no good than HMM, at least not too much good, better. And then the CRF come into play. So here I'm going to give you a very quick historical account. So the first kind of innovation over the HMM is to now at least allow global features to be included, and also to allow the conditional distribution of the label given the sequence directly modeled. Okay, so someone, actually not someone, he is a very good friend and a accomplished machine learning scientist, Andrew McCullen at UMass Amherst, together with some colleagues, proposed the following model. It's called the maximum entropy Markov model. We can ignore the maximum entropy story because it is a kind of a approach to motivate the design of the loss function. But now let's assume, remember that in one of our early lecture, we kind of say that if you want to apply a generalized linear model, it is equivalent to a maximum entropy argument. I think that's somehow written in the attached kind of the after class reading material. But regardless of that, we can basically say, by design, I want to model this conditional distribution P of y given x to be now a product of a local transitional probability. Okay, I still have this chain structure, and I respect that. But now I'm going to directly model the transitional probability between the y's, conditioning on the whole sequence of x, the whole sequence. And then you need to choose a model family, and for good reason, and for a principled inspiration from the maximum entropy principle, one can choose a log linear model or the generalized linear model in here. So here you have the weighted sum of all the features. These features are local, defined on a pair of states, and also the entire sequence. Okay, so I wouldn't comment on how exactly this feature will be designed. I think we visited that before. We can say certain states putting together will get some particular score and stuff like that, right? And the conditioning on the whole sequence being 10 character long, 10 word long, or 20 word long, their feature weight should be such and such. So that's pretty standard. And then because this whole thing is a valid conditional probability, therefore the whole thing has to norm to 1. Therefore there is this z, okay, partition function here. Okay, so that's pretty straightforward, right? We have now a model which satisfies the two kind of desires that we want to have. One is having non-local features. The other is directly model the conditional probability. Okay, so how good it is. So when this model was designed and the paper was published, and people find that the performance isn't dramatically dominating the HMM. Okay, for at the beginning unknown reason, but later people actually figured out something is going not quite right. So here I have a very interesting example. This example, if you read John Lafferty's original paper, it was actually articulated pretty nicely over there. It's called the labeling bias problem. Okay, and he used this word why we should award ROP is instead called a RIP due to a kind of a statistical reason that is beyond your control. It's intrinsically a flaw in the model design. And here I'm going to expose that problem a little bit more detail. So we have a sequence of observations, and say at every location we have a few hidden states. Okay, And remember, this model is to basically, it's about building this local transitional probability between the hidden states. Okay, so imagine you learned the model already. You learned it, and so this is what you learned. The first state, for whatever reason, is always bringing you to another two states. Okay, so with a probability 0.4 to this one, and it has no probability of going into any of the other three states. Okay, so that's basically something, imagine you learned from a training data. And the second state has another transition probability distribution. It basically, has a kind of a widely spread distribution over multiple downstream states. So now it has a equal probability of moving into 5 downstream states. Okay, and maybe slightly biased toward the second one, but it also has non-zero probability of moving to others. Right? So this is basically, imagine the numbers you just learned from training data. Okay, so nothing goes wrong, except that now you empirically observe that state 1 seems to almost always prefer to stay in here, in 2, because you can see at every time when there is a choice, it has a greater probability of going to state 2, okay, other than the last one, which has equal probability. And you also observe that the other state 2, if you are in state 2, what's going to happen? If you are in state 2, you are more likely to stay there, because you can see the transition probability between the state 2s are greater than the other alternatives. Right? So that's basically, when you learn a model, you want to inspect your model, and that basically is the high-level knowledge you get from the model. So nothing goes wrong so far. What's something going wrong is in the decoding state. Now you have a new sequence, and you want to decode it, use this model. And to people's surprise, the outcome of decoding isn't quite in agreement with what you're concluding here. Say state 1 always want to move you to state 2, and the state 2 always want to stay in state 2. Somehow what you learned failed to generate a kind of a consistent or decoding result that you expect to see. So for example, let's see here. We can actually compute that. Let's see a decoding outcome of multiple decoding outcome and compare which one is actually more likely during the decoding phase. So here we can compute the probability of a pass from 1 to 1 to 1 to 1. Okay? And you can multiply them together. It gives you a probability of 0.09. Okay, 0.09. So that's a probability of a pass. And here is another pass. We just stay in state 2. Okay, that one, if you multiply everything together, gives you a tiny probability of 0.018, which is roughly 1/6 of this one, smaller, right? And then you have maybe other passes like 1, 2, 1, 2, going here, 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 so on, and you compute that 0.06. And you can basically do a few such exercise, and at the end of the day, you will find that in fact the most likely path is this one. Okay, staying in state 1 always. Okay, and what you expect to see, which is when you are in state 1, you always want to move to state 2, and when you are in state 2, you always want to stay in state 2, did not happen. Okay, so this is a very strange behavior. People got confused a little bit. How come my empirical interpretation of the model failed to generate an outcome which is in agreement with my observation, right? So can anybody share with some insight why such a artifact happened? You want to say something? Yeah.
Question.
Yeah.
So we are also taking into account the emission probabilities of observation.
Oh yeah, emission. Well, actually, in fact, here there is no emission already, because remember we are learning this descriptive model where we only care about p of yt given yt minus 1 and all the sequence. So the emission is kind of already encoded in here because your transition is built on the entire sequence. So the observation is built in, right? This is arguably even more powerful than doing the emission, because in that case, you need to turn around, use Bayes' rule, and still generate this, but it's less direct. Right. So any comments on why this happened? This is very mysterious. Actually, this very artifact is what prevented me from understanding paper. I stared at the paper for almost a week, and I just don't know what's going on. Even though John, actually told this story, I think with at least 1 or 2 pages of text in the paper, I failed to understand that at that point.
Is it because it's directed?
No, directed. I don't believe so. Even if you go in, okay, you may be actually hitting a interesting spot. Can you elaborate why directed is causing a problem, and why do you see an indirect approach may lead to avoidance of the problem? Maybe a little bit deeper into the core. What is the statistical reason? Okay, that is making a difference. Everybody should feel free to chime in. Yeah, please.
Well, it seems like the reason is that locally it seems like you would expect that to happen, but the whole point of the model is that you're not looking at things locally.
Mm-hmm. Yes. Right. Okay. You are also getting a good point, which is closer to the core as well. There is this locality and global kind of trade-off between probabilities. So what's happening is the following. So here, for some reason, I have only 2 transitional events from here to here, okay, and this one, it is just spread across, all the transitional events into 5 different states. Therefore, even though this movement from 2 to 2 is very high locally, but if you compare this number to that number, it is still small. Basically, while entering an unfair game, that we use this probability to compare with that probability at a scenario where they shouldn't really be compared that way, right? Because what is important is, when I am in this state, what kind of decision I have to make. So I only need to look at my transitional probability of many options. But on the other hand, this one is in a different game. It only has 2 possible outcomes. So even though I'm having a smaller probability of moving to here, that smaller probability is still, in magnitude-wise, bigger than this one, right? So that's basically, generating a kind of a paradox of what you perceived as a kind of a local piece of knowledge, and then what you get as a result of improperly putting them into a global context. Okay, and this is called the labeling bias. And for that, you probably can understand why Rob and Rip get a very funny kind of undesirable treatment, right? So say from Rob to R2O, is a pretty natural kind of. This one is a pretty natural kind of a word. You actually probably see it more. And this one, you saw it, but it's not a great word. But why this one is very often favored over that? Okay, it is because when you are in I, the way you're transitioning out of the I may be fewer, just because your training sequence are not, often enough. You may see just a small training data set, or just because it's the nature of English that people don't put a lot of characters after I, right? Therefore, once you are in I already, no matter what you transition to, it is going to have a pretty good probability, okay? But in here, even though R to O has a very high probability, but O to anything else also has a lot of different options. Therefore, OB is a high probability transitioning, but the magnitude of that probability isn't as high as I to B for whatever good reason. Okay, and that's an artifact. What you really believe is that O to B is more likely than R to B, I to B, but they are calibrated in a different way. Yeah.
So if we take second order Markov, like look at the previous 2 states, not just 1 state, can this be solved?
That's of course you can somehow fix it, but that's a wrong kind of style. You just fix that variable. Then I say, well, in the second order, I have the same thing. I need to still transitioning. It's not a fundamental solution, basically. It fixes this one word to another, one character to another thing. How about two characters to others? Same thing, right? So it's not fundamentally solved the problem about calibrating the probability, right? So here is actually where, I don't know whether John Lafferty observed this artifact first and accordingly designed the model, or he came up with the model first and then go back and interpret the model in this way. But nevertheless, what happened is the following. He chose to now not normalizing the probability of every state, okay, locally. He basically just put them, as a numerical weight. For example, this one, it has the option to go to two states. I put them 2020 or 2030 just to showcase the relative magnitude, relative strength. And then for the other guy, who is also moving out, but into 5 possible destinations, I'm going to use not probability, but just use number, which are comparable in magnitude to the other things. Okay, so I put 20 here and 10 here, which at least now, I could have put here 30, right? But at least in here, I don't have this extreme case where I am basically 0.1 versus 0.4. And that's basically coming to our early design of the Markov field, right? We basically say we use potential instead of local probabilistic distribution to capture the local property. And the potential is a pre-probabilistic notion which does not have to be normalized. So with that, you kind of alleviate the problem, and mathematically it generates the following form. Instead of having this local normalizer for every local exponential family distribution, you are now, move this z out of the whole thing. And in here, you just have a product of this exponential form, okay, which are local potentials. And the feature strength can be 20, 30, or whatever. Basically, it only depends on the transitioning pair of the states plus the whole sequence. But the number itself is globally calibrated. Okay, and then they will be globally normalized once you put the whole thing together. So in here, it basically says that the transitioning from any state to the next state and in anywhere will have a strength that is globally comparable. Okay, they can be calibrated, and if you believe an event has a small probability from here to here, it can be used to compare with another event happening in here and between other states. Okay, so that technique kind of allows you to now begin with a true local design, but still have the global effect that you desired. Remember, one of the key advantage of graphic model is that we have a localist design. We don't have to worry global thing, and we design locally, and we hope this whole property is preserved globally when we do inference. And the example I showed you before kind of failed to deliver that. And then here you return to that kind of property. You design local features, you achieve a global effect which is consistent with what you hoped from a local inference. Okay?
So the normalization that we are doing here, would it be much more computationally complex than?
Yeah, you pay a cost. You pay a cost, yes. You do pay a cost, and as we said, Markov field is in general more complex than the direct graph model, but you never get free lunch because you have better power in this case. Right? Now, this is where the conditional random field model actually came from. Okay, that's a very nice history. I personally very enjoyed, and now I just want to put this up front. You have now two types of features, and you have the pairwise feature. You can also have the node feature, just to tell you how every single state are favored in the context, and you have a global normalizer. Right. So now I explained to you where the CRF come from, and the time to worry about inference. Right. So inference in a indirect graph model, we kind of tried a few kind of instances already, and here it's just a quick review. Right. Now, the inference problem involves getting the best labeling sequence or the best single label at a particular spot given the entire sequence. And this is equivalent to this argmax problem, right? And we know that the graphical structure is a junction tree, right? In the conditional random field case. And then what you really have are basically a chain of pairwise potentials, right? And how to compute the marginal of every pair, of every clique in here. So we learned message passing. That's basically, remember, our message passing algorithm was actually deployed on an undirected graph. Therefore, this is an undirected graph. If we have a direct graph, we need to make it undirected, and this one is already undirected. So we do forward pass and backward pass, and we basically get the whole solution, which basically gives you now you have a way of estimating yt and yt minus 1. You basically can compute this for every t. And what does this correspond to? Well, this corresponds to a p of yt minus 1 and t given x, right? It's just a proportional thing. You just normalize it, and you get it. Okay, remember now we have this already, and now we are entering the learning problem. The learning of CRF, as you can expect, is somewhat tricky because we spent the whole lecture talking about the learning of undirected graphic models. And we kind of already mentioned about this little caveat that learning in undirected graphic model, even they are fully observed, actually requires you to do some inference. Okay. Oh, by the way, in here, let me ask you one thing. I forgot to mention, but it's a good point to ask you. So on the training front, do you see a differences of the CRF versus HMM in terms of the training paradigm, supervised and unsupervised? Or maybe alternative I should ask is CRF and a supervised model or an unsupervised model? It must be supervised because by definition, you worry about now y given x. And if you don't even observe y, this whole problem is illegal, it's invalid, right? So it's a supervised learning problem. But yeah, again, even in such a supervised setting, learning can be tricky. Why it's tricky? Well, let's look at the exact definition of this learning problem. So learning in CRF amounts to figuring out the maximum likelihood estimation of these two coefficients, which are the pairwise marginal weight and the singleton marginal weight, right? And so here is the loss function, okay? And here you cannot really play the expected marginal likelihood, complete or anything. It is already fully observed. Therefore, this is the loss function. And then you are going to, and in this loss function, you already have something ugly, which is this guy, right? This is a function of all the parameters you have to estimate. So hopefully, with good faith, we're going to take a gradient over this guy. And now we have the gradient of lambda equal to this thing. You can actually derive the gradient over mu similarly, and they'll give you a similar structure. So how does this look like? On the first term, you have the feature, okay? And the feature is our design. We actually know that value already. Once you observe the training sequence, you can use the table lookup to get this value of the feature, right? The second term is somewhat strange. It asks you to compute what? What is this? This is the expectation of that feature, as if you don't observe that feature. Okay? What do I mean by don't observe? I mean, as if you didn't observe this exact instantiation of the y's. You have to compute, their expectation with respect to the conditional distribution of y given x. Okay? And that's why we need to, actually deal with inference problem, because in here, what you really meant to do is to now have a p of yt minus 1 Okay, here I use I, so I and y I minus n given x. You need to compute this, right? So that's basically pretty much written here. You need to, calculate this value. And okay, so do you know how to do this? 3 slides ago, I told you about the message passing algorithm to compute the pairwise potentials, which gives you, a closed form estimation of this pairwise conditional probability. Therefore, you need to bring that here to compute it. Okay. So that's why learning CRF involves a inference subroutine, and you're going to call it on and on to enable this computation of the expectation. All right, so luckily this problem become tractable because computing this one can be done in polynomial time using forward-backward, and then you are going to do this locally. All right, so and here is just an outline of a layout of the whole kind of algorithmic structure, and I think we can pretty much pass that. You begin by message passing procedure. And at the end of the day, you'll calibrate your message and you'll recover, the local conditional. All right. So I think I don't have anything left for this. That's basically a bunch of updated equations you need to use to learn the parameters. And I don't think there is anything interesting here. Oh, yeah, this is an interesting point. So here we are learning the coefficients, lambda and the mu. This is a little bit different from learning the multinomial probability. Remember, if we express the conditional in a table, we are going to estimate those probability with relative counts. And there we have a technique we call smoothing. And then later we say it is actually a Bayesian story. You can define a prior, and that basically gives you a way to regularize or to smooth the estimator, right? It pretty much avoids you to get strange number like a zero probability or stuff like that. Well, similar treatment also happens in here. Now you are estimating a continuous number, and it is trendy, maybe numerically stable, to apply a Gaussian prior for each of these little estimation. Okay, so that's what you're seeing here. Okay, this is called Gaussian regularizer. It is trying to. So what is the role of that? It is basically trying to say you can define a prior distribution of the beta, of the lambda, and a priori, before you see anything, you want the estimation to centered over 0, and with a small probability to be away from 0. What does that mean? It means that only if the estimation coming from here has a strong evidence of being non-zero, that lambda should be 0. So this is opposite to the conditional probability table estimation. There, we don't want to see 0. Why? Because a 0 probability event is no good. In here, we want to see more 0. Why? Because having zeros meaning that we have a fewer feature to deal with. Okay, you don't have to actually maintain a big list of features, many of which can be useless. And in here, you have a automatic kind of a feature specification approach. So for that reason, this Gaussian prior can be also a Laplace prior, right, where you have a slightly different density function, which push you even further into the 0 case. Okay, and with that doesn't really change anything in your estimation procedure. You just have a small kind of correction over your gradient, and you use the same algorithm you did before. All right, and there are some algorithmic tricks to speed up this algorithm, which I'm not going to talk about. So this whole material is very nicely presented in one of the paper I posted on the website. That's by Fei Sha and Fernando Pereira on this. I forgot the title of that. It's a speech recognition type of application. But in that paper, all the equations and the derivation was presented very clearly. Okay. That's actually how I actually made sure that I completely understand the details in the procedure. Okay, it's a little bit better written, easier to understand than the original John's paper. All right, so performance-wise, I have to say it's a little bit underwhelming. It's not like you see a 50% jump in the performance number as a result of new model. Okay, so here these are the very honest graph showing a side-by-side pair, head-on comparison between any pair of opponents, and MM versus CRF. Okay, this is categorically worse, and MMM over HMM, they are comparable, and CRF versus HMM, somehow there is a split of regime. In this regime, HMM is better. In this regime, CRF is better. Not by too much. Okay, and of course there is an intuition behind this pattern. Here, once you go that direction, the order of the data is bigger. Okay, you have a longer and longer sequences, which kind of imply the non-local effects is playing bigger and bigger role. And if you have a right way to capture that, you win. And therefore, CRF in this case does generate a slightly better result. In terms of number, not very impressive. The bare bone CRF is 1%, not 1%, 0.1% better than the HMM. Okay. Again, I have to say that it's very thankful that the paper can be published with this result. But nowadays, I think the reviewers are much more greedy in seeing a better performance boost. If you don't have a 10% over the past, you probably don't get a publication. But I think that the value of this improvement is really, really substantial, because it opens a new modeling paradigm for a very wide range of different problems. And also, CRF model had a lot of flexibility. That's actually something that HMM does not have. Right? Look at this. So here, because CRF is a feature-based model, you can design arbitrary features you want. So what they did, for example, is to maybe inject some additional features, spelling features. I don't actually know what spelling features are, but I imagine it must be something very clever. And just by putting some new features, the performance gets a huge boost. Okay. And the truth is that if you play with HMM, even if you have those features, you have no way to make use of them. There is no kind of a device for you to incorporate this feature. Right? So that's actually what makes the CRF a really attractive model for many applications. And now that I have still 20 minutes, we can go through some case study, okay, to see some substantial CRF applications. Yeah, questions?
I just couldn't understand why you said CRFs are supervised. And, like, we can do unsupervised POS tagging using HMM.
Yes.
Can we not do that using CRF?
No. Just, if you look at, so here is the way I understand that. If you look at the CRF, it is the modeling P of x given y, right? And the way you write it down is basically the exponential of sum of some features, sum of some features, divided by this, right? And now I invite you to to think about what's the form of a logistic regression. It's the same as this, okay? And logistic regression, can you do it? The definition of a unsupervised logistic regression doesn't exist, right? Because you are explicitly maximizing the conditional probability of the label given the data. And if you don't even have the label, then you don't have the loss function, okay? There are some weird setting where you could imagine a artificial unsupervised scenario where maybe over this entire sequence, I have something observed, something not observed, but they have some alignment. let's take a look of some fun CRF models that is now widely practiced. Okay, I think the computer vision people particularly like CRF because, as you probably know, the holy grail of computer vision is about playing with features, right? In fact, the computer vision community really are not very happy with the machine learning research because they thought we've been too detached from the real data and from the real problem, and we were building models all the time, right? So for a long time there isn't a lot of interaction between machine learning and computer vision. But I think CRF is the single most kind of successful machine learning product that has been practiced in computer vision because you see this perfect interface of modeling and feature design. Okay, so I'm going to actually show you where they are practiced and how they can be practiced. So the first extension is that the CRF, okay, it's called the conditional random field. Random field is, of course, not limited to a chain. Okay, it can be a grid. Therefore, one first extension people do is this. Okay, but this graph itself is a little bit kind of ill-positioned. Okay, so what do you see wrong with this graph? Every node can have a particular node, which is kind of the observation or some features, right? At least from the way it looks like this is a pretty localized model, right? Yeah. It is actually not emission, but it looks like emission, so that you may get the confusion or get the illusion that this little black node is a local feature. Okay. But if you are a master of really playing CRF, like Michelle Herbert in here, they actually are treating this one as anything. Okay, this little node can gather information from the entire image or something, even though I put it here. Okay, so that's basically what I want you to want to demystify from this graph. It is not necessarily a local thing, and in fact, I'm going to give you a few examples of how this can be played. By the way, for this bigger model, there are some additional challenges that requires actually a good amount of machine learning research, and that's where I think I would say computer vision research would need some help from the ML people, but such a exchange isn't happening very nicely yet. So for example, this is a great model, and how do you do inference? We kind of studied before that. So the junction tree of this type of model is as big as an entire front of this grid. And the entire front can be a few hundred pixels. If it is a few hundred pixels, you can imagine how big is the problem. It is totally intractable, right? And therefore, you need to use approximate inference, as we're going to cover in the next few lectures. And there is a variety of choices of approximate inference. Here I have some names here: MC sampling, variational inference, loopy belief. We're going to study all that down the road. But they actually have their comfortable zone. Some are good for certain models, some are not. It turns out that in applied research in vision and in many other domains, people, I hope that doesn't happen to you. There is a confusion in terms of evaluating a method. Okay, the method actually is not necessarily a model or an algorithm. It's the whole thing. For example, I'm going to, use a MRF or a CRF to model a computer vision problem, and at the end of the day, I failed. The performance isn't good. Then what should we say? The simplest thing is that, okay, this model is terrible. I'm going to use another model. A more sophisticated way of investigating is the following. You are going to use this model and then try a bunch of different inference algorithms. Maybe try an exact inference algorithm at a greater cost, but you do it only once. And because it is exact inference, at least you don't make mistake on the inference side. Then if it is still is working wrong, then that means the model is incorrect, right? But on the other hand, if if you do good inference, the performance become very good. If you do bad inference, the performance dropped. That kind of suggests the model is actually correct, but your inference algorithm is terrible. And that's actually what frustrates me quite a bit when I talk to many practitioners. they would openly say, hey, your graphic model is terrible, or some model is terrible, and then I'm going to switch back to a simple model, say k-nearest neighbor. Okay, but if you interrogate the guy a little bit deeper, say, hey, what inference algorithm you used? He may say something outrageous. He will say maybe, oh, I used a naive mean field to infer this. Well, I tell you in the next few slides, lectures, naive mean field is the worst type of algorithm to do this kind of inference, because the holy grail in naive mean field is to now disconnect all these edges, make them independent. Then at least the very purpose of building a connected model, right? So that's actually an important lesson I want you guys to get out of this class. There's an interplay between the algorithm and the model. Okay, to justify whether an approach is working or not, you have to study both the model and the inference. And that's why in my own work or somebody's work on, for example, topic model and other things, it might not be enough just to show, hey, I run a topic model on some corpus, I show some nice topic, and the other guy shows some different topic, all claim success. You actually need to do some simulation and make sure that your inference algorithm is correct. And then you can make a statement about the quality of the model and so on. Right? So these are the kind of lessons I want you to get down the road, and we're going to maybe get our initial encounters of such a problem in the next few stories. So let's look at this model. I think CRF find one of the greatest success outside of NLP in computer vision for image segmentation problems. And the problem is very familiar, right? You have this input image, and you want to really do a pixel-wise separation, okay, of the foreground from the background, right? And how do you do that, right? So the image can be very noisy, and there are, but there are kind of nice assumptions you can make on the image. At least if you call something an object, you kind of assume they are contiguous, right? Although there are fancy, more complex situations where occlusion happens. I mean, something in front of that happened, then this object can be discontinuous. But that's the special case. You need to put other model ingredient. And then, this is the true kind of segmentation. But what if you get this? This is reasonably satisfactory. You kind of can recognize already a duck type of thing in here, right? And so this is because of the assumption, and but it is arguably a correct kind of compromise that you can do for segmentation. So how to do that? Well, one way to do that is to turn it into a labeling problem, a pixel labeling problem, that for every image, every pixel in the image, you associate that with a label called Y, okay? And it can be a binary label, just background and a foreground. And then depending on it is a background and a foreground, you design a feature, okay? A feature. So this one, what does it say? It pretty much means that if the background is so on and so forth, my label, say if the background is green, my label has a stronger tendency of being both background and a weaker tendency of being the foreground. And this is a pairwise feature, which, okay, so here they put it just the YY, which means that I want to have a contiguous label. The YI and 1J, if they are adjacent, they should have a similar label, and otherwise they should not. But you can make it even more kind of aggressive. You can put an X here to say if the background takes certain, if the feature takes certain, if the global feature has a certain color, then I'm going to favor a pairwise more strongly or less strongly. Right? So at the end of the day, you can write down this entire model. Of course, here some weights are missing. In fact, all this reflects a history of how the vision people are learning graphical models. They kind of start gradually into the domain and learn some essence, but forget about some details. For example, here the weights is not carved out separately, and these are just notational convention, very familiar to the graphic model people, gradually entering other domains. So then what you can do is to set up a loss function, okay, and you have two choices. One is a MRF, one is a CRF, and again at the beginning, you actually see such two choices. If you are very experienced, you probably, it's a no-brainer that you want to rule out MRF because the MRF, is just a, CRF is actually the way MRF should be practiced rather than what they call MRF. Basically, their definition of MRF that you have all this X to be a local thing from the very pixel that is hanging off that particular label, and that's called the MRF. But in fact, CRF is also an MRF. Therefore, there isn't really a point of distinguishing these two, right?
So what
yeah.
is the supervised data here?
What's that?
What's the supervised?
The supervised,
Yeah.
well, I give you an image. I draw this region already. I told you this is background, this is a foreground. Then every pixel gets labeled already.
Oh, so there is a supervised.
Yeah, yeah. You must train it with such labeled image. That's why you see on the, Amazon Mechanical Turk, there are very often little exercise for the Turkers to label images, right? That's the goal for the purpose is to generate this kind of data. Okay, so you have all this set up, and then you maximize the conditional probability of a p y given x, right? And yeah, so here, for some reason, the vision community made a big deal between the differences of a MRF and a CRF, and by definition, the MRF is using this type of design, where you have a local emission of the feature. This is, again, by the way, not in the kind of the general definition of MRF way machine learning people considers. Okay, this is their form of MRF because, in my opinion, this is just one way of defining MRF. There are more general ways of doing that. But nevertheless, it makes a point in that one way of designing a MRF is a localist way, where you only employ this local feature, okay? And therefore, the graphical model draw like this. Literally, it means this node is the feature from that particular region, okay? And then, just to make the contrast, they call a CRF, which is actually also a MRF, okay? And they want to make a point that it is a different design by saying, now my conditional of the y is conditioning on the entire x. Okay, therefore, any label of y is potentially connecting to every other nodes in the graph, in the image. Yeah, in fact, this kind of confusing-looking graph isn't helping at all, because at the end of the day, you still have every y hang off some particular feature. No matter how much they connect it, they are already observed. Therefore, they all group together into a single node. You don't have to worry about this graphical structure in here. Okay, the graphical structure at this direction isn't influence your inference, because they are all observed already. Right. All right, and then of course there is a obvious trade-off and a difference between this what they called in the CRF and MRF. Right, one is a local feature, the other is a global feature, and you'll see a performance actually differences. Which one is better if you were to choose? Right. So I believe I have some graphs here. Do I have the results? Oh, okay. So no, not. So this is. I meant to show you the results of this and that, but in fact they brought in a third comparison, third model, which they called the DRF. Okay. It's called a discriminative random field. Again, I want to point out to you, DRF, CRF, and MRF are all MRF. Okay. It's just a different design of the potential function. So remember, in a macro-random field, you have the freedom of designing this. Okay. The three models that you see are just three different choices of this guy. Okay. They are the same model with different choices of features. But confusing enough, it's called, unfortunately, three different names. So sometimes when the whole thing gets back to machine learning community and to the inexperienced student, they start to get a wrong dose of message, thinking, indeed, that's three different models. But I found this DRF quite interesting because it uses a very, very, very smart way of designing this feature, okay, which actually, I have to say it's quite ingenious. It's by, Marshall Herbert also in here. So they call it a discriminative macro-random field because they actually have a very specific way of designing the feature, not based on any ad hoc kind of score number. Say I want that feature to be strong and this feature to be weak and so on and so forth. They are actually trained features. The features are trained in a pre-processing step. For example, in this one, this is the singleton feature, which tells you the association of the label with the feature. They actually, define that feature to be itself a logistic regression. Okay, and it's reasonable. Basically, it is a classification problem that whether this pixel is background or foreground or object 1 or object 2, right? And the input is the features, centered in that partition, but around that as well. And that's actually a classification problem, right? And if you have enough such, carved pictures so that you have exact supervision from the data, you can actually train this potential function. That's actually a very interesting concept. You can train the potential function, okay, using this logistic function, and that's what they did. Similarly, you can train the pairwise potential function because now it's about seeing the background or seeing the global feature. What is your assessment of a pair of labels to behave? Right? They should be labeled in a similar way, or they should be labeled in a different way. So here they have this this particular formation. Right? Of course, here they assume the y's are binary, 0 and 1. Therefore, you can basically, actually, I believe it is a +1 and -1, so that you can see the parity. If they are different, they generate you a -1. If they are identically labeled, they generate a 1. And in here, you have even some more crazy ideas. So not only it is a logistic function that is trained from prediction, it also has another component in here, which is the smoothing effect. Okay, they call it data-independent smoothing. And this is a data-dependent pairwise logistic function. Right? It's almost like here you have a prior that without seeing anything, I believe the label being similar to each other should take some weights, even before I see anything. Then if I see more things, I can violate it if I see a strong evidence, but I can agree with it if I see whatever, weaker evidence or nothing. Right? So this is a third design of the potential function at the end of the day. I think it is the grand kind of competition. You have the input image, and their goal is to do something even beyond just a binary segmentation. They want to almost use this as a object detection tool, right? To maybe find out where the house is. Right? So the design was, you can of course go fine grain by labeling every pixel, meaning that for this maybe 225 and the 225 pixel, you can put every pixel a label. But what they did is to make them a 16 by 16 tile blocks. Okay, and for each of them, you can collect feature and give them a label. So now you can see the differences. So this is the input. Okay, and what's happening here is called the logistic regression. What does that mean? It means that for every block in here, you just do a classification, whether it is a foreground or background, just regardless of the context. Okay, you don't care about the context, so it is a complete local inference, and as a result, you see, all this anything that with some kind of texture is regarded now as the house. Okay, the sky gets kind of easy. So, but on the other hand, there are some noises like these trees are correctly labeled, but these trees become to be labeled by a house. And the MRF, the difference is that you still use local features, okay, but your way of labeling gets coupled. Pairwise, adjacent labels seems to be together and to be consistent. Therefore, you are now seeing contiguous blocks of labels, right? Here you have a singleton, foreground label. Here you almost never see a singleton label except here. But everything else becomes a contiguous block. That kind of plays the effect of a MRF. And what they call the DRF is just another MRF with some fancy features. And you can see the performance gets obviously better for two reasons. One is because your feature becomes global. The other is that your feature is a distributive feature, which is trained. in their very ingenious way. What I'm curious to see is what they call a CRF in here, which is unfortunately not. So I want to see the effect of that distributed training of the feature, the effect of that, but it's not played here. But so this is a very good example to show you how flexible you can go with this whole CRF infrastructure. And now you know what you should do, right? If you get some nice application problem, in your little computer vision project or many other, NLP and biology project, you can pretty much set up the same thing, and make your training or make your prediction, a structural prediction, much more principled. All right, I think I'm about to time, and there's a second example you can go over for fun. It's for body pose estimation. Same thing, you are going to build a CRF which captures, the body formation and the relationship. The head must be on top of the shoulder, and the forehand must be after the back, the shoulder as well, and stuff like that. And at the end of the day, you can build a model with pretty much the same principle we see before. All right, so with that, here's a summary. This CRF is a distributed model, right? And it overcomes some of the little pitfalls and artifacts in HMM and in MEMM model, especially the labeling bias problem. And you can deploy CRF to 1D, 2D, 3D, high-dimensional problems, if you will, and you can do learning and inference exact if you have a chain structure. You have to do approximate inference. You have an arbitrary structure, and you see a lot of applications already in different domains. All right, any other questions? Good. No class for next Wednesday, but on Monday we're still on. Please make sure to come. Thanks.